Welcome to this lecture on Elements of Mechanical Engineering, which is a course offered for aeronautical and civil engineering students. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. We are in the first module where we are studying different forms of energy and basics of thermodynamics. In the previous lectures, we have seen what are the different types of properties that are related to a system when we study the system under thermodynamics. So there are different forms of energy, there are different thermodynamic laws which are to be studied after the different properties. So in this lecture, we are going to see what are the different laws of thermodynamics. First of all, thermodynamics is the study of a body or a system which is undergoing some kind of temperature change. The temperature change may be because of the heat addition or heat removal from the body. The different properties like internal energy, enthalpy, entropy, etc. will be changed when the body is being subjected to thermodynamic study. So simply the word thermodynamic refers to the study of the body when it is undergoing some temperature change. So we have to use some laws, or some laws are defined in the literature where we have to use these laws for defining the state of the body or for using these thermodynamic study and use it for different applications. So thermodynamic laws define the fundamental physical quantities like energy, temperature and entropy. So these three important properties are defined by using different laws of thermodynamics. So they will characterize the thermodynamic system as thermal equilibrium. So whenever we take a system, when the system is said to be under thermal equilibrium, so then the properties are studied at that point where we can understand how different parts of the system is behaving in different states. Now, these thermodynamic laws represent how these quantities behave under various circumstances. Different circumstances, the thermodynamic system will behave differently. Now, there are four laws of thermodynamics, which are we are going to study each of them. So that is first zeroth law, first law, second law, and third law. So these are the four laws based on which any thermodynamic system can be studied, and it can be calculated by the parameters by using these four laws. So we'll see all these laws in detail. So the first one is zeroth law of thermodynamics. So the zeroth law of thermodynamics states that if two bodies are individually in equilibrium with a separate third body, then first two bodies are also in thermal equilibrium with each other. So in the given picture we can see zeroth law of thermodynamics is very simple to understand. Suppose I have three objects, like in this picture I have three objects are there. So this is first container, it has some water in it, and this is second container, it has also some water. Now I have third device here, this is a thermometer which is used to measure the temperature of any liquid or solid. Now we are going to use these three objects are used to explain the zeroth law. Now what happens is, suppose I have taken the thermometer and I have kept this thermometer in first beaker, that is beaker A. Okay, I have kept the thermometer in the first container. So what it will do is, it will rise the temperature or it will show the temperature like some, maybe if the liquid is at room temperature, it will show like 25 degrees centigrade. Now what happens is, I will remove the thermometer from first container and I will keep that in the second container. Now it will show the temperature is also around 25 degrees centigrade. Now what happens is, the contents in the first container are in thermal equilibrium with the thermometer. First A and C. I am representing the thermometer with the C. Now A and C are in equilibrium with each other. That means the temperature of the container, the contents in the container made the temperature inside the thermometer equal to 25 degrees centigrade. So the objects A and C are in thermal equilibrium. And after that, I have kept the thermometer in the second container, which both of them became thermally equilibrium by raising the temperature to 25 degrees centigrade. So here also the temperature is 25 degrees centigrade. Now the objects B and C are in thermal equilibrium. Now what I will do is, we can see there is a common thing in these two comparisons. In the first condition, A and C are in equilibrium. In the second condition, B and C are in equilibrium. In both these conditions, C is common, that is the thermometer is common. Okay, we are comparing the temperature of beaker A and beaker B with the thermometer, which is making the thermometer equal. The temperature is equal to the container's temperature. Now what happens is, here AC is in thermal equilibrium and BC is also in thermal equilibrium. Now we can simply say AB is also in thermal equilibrium. Okay. These two are in thermal equilibrium and these two are also in thermal equilibrium. Now what is the zeroth law is stating that these two objects like A and B containers are also in thermal equilibrium. Okay. So this is the basic definition of zeroth law. If two bodies are thermal equilibrium with a third body, the first two bodies are also in the thermal equilibrium with each other. This means if a system A is thermal equilibrium with the system C and system B is also in thermal equilibrium with system C, then system A and B are also in thermal equilibrium. So this is the basic definition of zeroth law of thermodynamics. Okay. So we'll go to the next slide. So far we have seen what is the zeroth law. Now we are going to see the first law of thermodynamics. First law of thermodynamics is also known as law of conservation of energy. So what is conservation of energy? So the law of conservation of energy states that the energy neither be created nor be destroyed, but it is converted from one form to another form. So if we take the entire universe, the energy or matter, it is not destroyed or created. It is only converted from one form to another form. It is not created or destroyed. Okay. Now the first law of thermodynamics follows the law of conservation of energy, which states that energy can neither be created or destroyed, but it is changed from one form to another. So let us take an example for this first law of thermodynamics where we can understand this concept. So suppose we take the example of plants. Now what happens? Plants will convert the radiant energy, that is the sunlight, will be converted into chemical through a process called photosynthesis. We all know that plants will follow this photosynthesis process for generating food. Now it will use the sunlight and it will convert the sunlight and carbon dioxide and some water. It will convert them into food. And we as human beings, we eat these plants where the chemical energy is converted into kinetic energy, which is used in the human body. And we can use this energy to do some activities like swimming, walking, breathing, etc. So the radiant energy that is coming from the sun is first taken by the plants. It has stored the energy in a different form, like in the form of chlorophyll. Now this chlorophyll, which is stored in the plant as a green colored matter, and we will use these plants for eating the fruits or something, the fruits or vegetables. Now we will get some energy from these vegetables and fruits in the form of kinetic energy, and we will use this energy for for walking, swimming, etc. So this is where we can simply understand the energy from the sun is converted into different forms, but it is not destroyed. It is converted from one form to another form, and finally it is reaching human beings, and we are using that energy for doing some activities like swimming, walking, etc. And second example for first law of thermodynamics is switching on light may seem to produce energy, but it is electrical energy that is converted. So in the night time, when we switch on a electric bulb, what happens? The electrical energy will be sent into the bulb and the bulb will glow. Now, generally what we do is, we are using some 5 bulbs in our house. We will simply calculate how much amount of electricity is being utilized. Now, we don't think about how that electricity is being converted into light energy, that is with the help of a bulb, but the energy, the electrical energy is being converted into light energy. We are not consuming the electricity, we are converting the electricity into light source. So this is what the first law of thermodynamics states. The energy is neither be created nor be destroyed, but converted from one form to another form. Now in the picture we can see we have a container. Inside of the container there are some quantity of liquid is there. Now this liquid, when it is compressed, what happens? The volume of the liquid will decrease. We are not changing the state of the matter. We are making the molecules to come closer. Now by doing this, we will increase some heat in the system. When we apply some pressure, the volume will be decreased. As a result, some work is being done on the system. So we have to do some work for applying the pressure on the water in the container. So we have to do some work on the system. While we are doing some work, some kind of heat will be generated in the system because the volume is decreased. The molecules will be moving closer together and the temperature will rise, which indicates some kind of heat will be induced in the body, induced in the system. So we can simply write the equation for thermodynamical first law as this: delta U is equal to delta Q minus W. So delta U is nothing but internal energy, which is equal to delta Q, which is the heat supplied or taken from the system, minus W. So W is the work done on the system. So this equation is derived from the first law of thermodynamics. Okay. So the first law of thermodynamics states law of conservation of energy, where we have to we only convert the energy from one form to another form, but we are not creating or destroying it. So the first law also indicates the equation delta U is equal to delta Q, that means change in heat transfer, minus work done. Now we'll see what are the applications of first law of thermodynamics. So the first law of thermodynamics is used for calculating the latent heat of vaporization. So when we are using water for creating vapor, vapor is nothing but the steam. So this vapor is used in the thermodynamic system called a steam power plant will be there. For the running of the steam power plant, we have to use the steam coming out of the water when it is boiled up to its boiling point. So when the water is being converted into vapor, we have to calculate how much amount of heat is supplied in order to do the steaming process. So how much amount of heat we have to supply to this process for converting water into vapor. So this heat is calculated by using the first law of thermodynamics. So how much amount of energy is supplied to the water is calculated with the help of first law. And the second application is, it is used to calculate the quantity of energy required to rise the temperature of an ideal gas about 1 degree. So this is also calculated based on the first law of thermodynamics. If I take a quantity of if I take a gas in a closed system, and if I am continuously supplying some heat, if I want to increase the temperature of the gas about 1 degree, like if the temperature initially is 25 degrees centigrade, now I want to increase the temperature to 26 degrees centigrade. How much amount of energy I have to supply to the gas in order to do this? So that is also calculated with the help of first law of thermodynamics. And third one is, it is used in the working of heat engine. We know heat engine is the ideal engine where we are going to use some energy for creating mechanical energy. Like all the engines work on this heat engine process. So the first law of thermodynamics is the base for all the internal combustion engines or external combustion engines, where we are going to convert the chemical energy or heat energy of the fuel into mechanical energy. And fourth application is it is used in the refrigeration systems. So in refrigeration systems, we have a system where we will convert the temperature or we will reduce the temperature by using some kind of a device called compressor. So this entire thing is called refrigeration. So it is also developed based on the first law of thermodynamics. And fifth example or application is simply sweating from human body is also first law of thermodynamics, because when we experience heat, we will generate some sweat from the body. So the sweating will cool down the body in order to keep the body in a certain temperature, so that we will not subject it to high temperature. We will sweat and we will cool down the body. So this basic thing from which is happening in the human body is also based on the first law of thermodynamics. We are converting the form. We are converting the form of energy. So these are applications of first law of thermodynamics. Next, we'll see what are the limitations of first law of thermodynamics. Even though the first law is based on many applications, still first law of thermodynamics have some limitations where this first law has to be developed or modified in order to apply in more fields. So let us see some of the limitations of first law of thermodynamics. First one is the first law of thermodynamics fails to give the feasibility of the process or change of the state of the system undergoes. So first law cannot give the information about how the system is undergoing the change of state, how the system is changing from one state to another state. This information cannot be generated or cannot be calculated with the help of first law of thermodynamics. We can simply say how the energy is being converted from one form to another form. Like we will give some work, it is converted into heat or entropy. So this is the basic definition given by first law of thermodynamics, because of which we cannot give the idea about how the system is changing its state. And second limitation is it fails to explain the direction of heat flow. So first law of thermodynamics does not indicate in which direction the heat is being applied. Suppose I have taken a system, when I am heating the system, the first law of thermodynamics does not care about the direction in which the body is being heated. That is, the heat is supplied from outside to inside or from inside to outside. It only takes into consideration how the energy is being converted, but not consider about the direction. And then third one is, it does not say the process is a spontaneous or non-spontaneous process. Whether a process is spontaneously happening or non-spontaneously happening, the system will not understand based on the first law of thermodynamics. So these are the limitations of thermodynamics. So in the picture we can see whether the heat is being supplied to a body from low temperature to high temperature. This is the standard thing which will be done generally. Okay. Now, what happens if the temperature is being generated from high temperature body to low temperature body? This is not given by the first law of thermodynamics. Okay. So there are some limitations where we have to develop this first law of thermodynamics for better applications. Now, we'll see the second law of thermodynamics. First of all, we'll see the statement of second law of thermodynamics. So the second law of thermodynamics states that entropy in an isolated system always increases. Any isolated system spontaneously evolves towards the thermal equilibrium, the state of the maximum entropy of the system. So the second law of thermodynamics directly indicating the entropy of the system. So if I take the example of an isolated system, the entropy in this isolated system will always increases. First of all, we should remember what is entropy. Entropy is nothing but the degree of disorderness, how randomly the molecules in a system are arranged. Now, if I take an isolated system, the degree of disorderness will always increases. So this is the basic definition given by the second law of thermodynamics. Okay. Now, when we are studying the entropy, we have seen the random arrangement of the molecules in the system. Now, we'll see visualizing the second law of thermodynamics. Okay. Now, we have an example here. If a room is not cleaned, suppose I am taking the very general example for explaining this second law of thermodynamics. If I have a room which is not cleaned, so what happens? Day after day, the dust will become more inside the room and it invariably becomes more messy and disorderly with time. So if I am not cleaning the room for like 1 month, all the dust will be accumulated inside the room and it will become more messy and disorderly manner. Now, when the room is cleaned, after 1 month, when I try to clean the room, its entropy decreases. Now, what I am doing is the randomly arranged objects inside the room are cleaned after 1 month when there is high entropy. After 1 month of time, when I did not clean the room will have more entropy. That means the molecules or atoms are randomly arranged inside the room. Now, after 1 month, when I try to clean, the entropy will decrease because I am trying to rearrange all the molecules. I am trying to clean the room. The entropy will automatically decreases because I am uniformly distributing or arranging the molecules or atoms inside the system. Now, but the effort to clean it has resulted in increased entropy outside the room exceeding the entropy lost. Now, what happens is when I try to clean the room inside, the effort to clean the room that is being applied on the outside of the room will increase when compared to the entropy lost inside the room. So, now we are gradually coming back to the thermodynamic system. When I try to, suppose I have a system, isolated system, the entropy is very high in this system. Now, if I try to change the entropy or decrease the entropy, I will apply some heat or energy from the outside. Now, what happens is when I am trying to apply energy from outside or when I supply heat from outside, what happens is the entropy on the outside of the body, outside of the thermodynamic system, will increase, whereas the entropy inside the system will decrease. So, this is the basic definition or basic example for which we can understand the visualization of second law of thermodynamics. Okay. When we try to clean the room from outside, we have to apply some energy on the outside, which will increase the entropy on the outside, but inside the entropy will decrease because we are uniformly arranging the elements. Now, in this picture, we can see, so this is a uniform arrangement of the bricks and this is random arrangement of the bricks. So, this is general for given for visualization of the second law of thermodynamics. So, this is the basic visualization of entropy. Okay. So, this is the second law of thermodynamics. So, we'll see where this second law of thermodynamics is applied. So, second law of thermodynamics has many applications like it is mostly used in internal combustion engines. So, there are many cycles like Otto cycle, diesel cycle, and all these cycles will make the IC engines work. Otto cycle is directly related to petrol engine and diesel cycle is related to diesel engine, where the working of these cycles will make the energy to. So, the Otto cycle and diesel cycle as well as the working fluids employed in the engines are covered by this rule. Okay. Modern automobiles have advanced as results of this law. So, all the internal combustion engines are directly related to are based on the second law of thermodynamics. Now, we have another example, that is another illustration of how this idea is used in reverse cycle refrigerators and heat pumps. So, the second law also employs the usage of refrigerators and heat pumps. So, these are also applications of the second law of thermodynamics, where we are going to use different kinds of refrigeration systems and heat engines. Heat pumps are also developed based on the second law of thermodynamics. Now we'll see in detail. If you want to move heat from a body with a lower temperature to a body with higher temperature, we must protect external work. The original Carnot cycle uses heat to create work. Now, we know that from our basic knowledge, heat always flows from hot body to cold body. Hot body to cold body. Now, if I want to remove the or if I want to move the heat from cold body to hot body in reverse direction, I have to use some kind of device. So, the working of this device is called as compressor. The working of this compressor is based on the second law of thermodynamics, where we will do some external entropy work for distributing or uniformly distributing the internal entropy. We have seen before, the entropy outside the system will be more when compared to inside the system when we are trying to decrease the entropy. So the refrigeration systems, heat pumps, IC engines, all these machines works on the second law of thermodynamics. Okay, we have some cycles. Carnot cycles uses heat to create work. Carnot cycle is there, as opposed to reversal Carnot cycle, which transfers heat from a lower temperature reservoir to a higher temperature reservoir using work. So we cannot move the heat from low temperature reservoir to high temperature reservoir generally with our basic knowledge. But using the second law of thermodynamics, we will devise the temperature from low cold body to hot body. We can supply heat from cold body to hot body. Now, so this is the applications of second law of thermodynamics. Now we'll see what are the limitations of second law of thermodynamics. What are the limitations? So the limitations are the second law of thermodynamics only deals with irreversibility of heat conversion to another form. So when I am using the second law of thermodynamics, so the thermodynamical second law will tell you irreversibility of heat conversion to another form. But the second law of thermodynamics only deals with closed systems. So when I want to apply the thermodynamics second law to an open system, I cannot use this system. I cannot apply this law to the open system. I can apply to this only closed system. That is why all the IC engines, that means internal combustion engines, where the combustion happens inside the engine, inside a closed chamber. So these engines, the second law can be easily applied. Okay. So the second law is only possible for closed systems. For application or the usage of external combustion engines, the second law of thermodynamics is no longer valid. Now, so these are the limitations of second law of thermodynamics. Now we'll see what is the third law and how this third law is used in the outside world. Third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. Now in the previous lectures, we have seen what is an absolute zero temperature. Absolute zero temperature, mostly the Kelvin scale absolute zero temperature is taken into consideration, where no electronics will work at this temperature. That is, we have to use a gas thermometer for measuring the absolute zero temperature. No electronics will work. That is, that absolute zero temperature is nothing but minus 273 degrees centigrade or 0 Kelvin. These two are same. Minus 273 degrees centigrade is the temperature where we have to use a gas thermometer for measuring this temperature. Okay. So the third law of thermodynamics states that entropy of a system approaches a constant value when the temperature approaches absolute zero. When the temperature of the system is reaching 0 degree Kelvin, then the entropy of the system will remains constant. So the entropy, there will be no disorderliness in the system. So this is the basic definition of third law of thermodynamics. Now we'll see what are the examples so that we can understand better. So the first example here is the molecules within the system will move freely and have high entropy. So this is one example where the molecules inside the system will move freely and have high entropy due to this temperature, but the entropy is constant. It will have some entropy, but it will not change, it will not increase or decrease. The second example is if one decreases the temperature below 100 degrees centigrade, the steam gets converted to water where the movement of the molecules is restricted, decreasing the entropy of water. Suppose I have water, I have boiled the water up to 100 degrees centigrade. What happens? 100 degrees centigrade is the boiling point of the water where the water will be converted into steam. Now what happens is the steam, now when it is cooled, it will be converted into water. Now what is happening inside the water molecules? So the movement of the molecules is restricted here. So the movement of the molecules is restricted, which means the free molecules in the system, the steam, will be stopped moving and they will decrease the entropy of the water. Okay, the entropy of the water is decreased so that the steam will be converted back into water. And then third point is different types of vehicles such as planes, trucks and ships work on the basis of second law of thermodynamics. Okay, different engines will be there, planes, trucks and ships. These are all based on the working of third law of thermodynamics. Okay, and then fourth example is the three modes of heat transfer works on the basis of thermodynamics. Now, in heat transfer, we have three modes, that is conduction, convection and radiation. So these are the three forms of heat transfer where heat is transferred from one body to another body. Now these three forms will be based on the third law of thermodynamics. So when we are studying heat transfer, the basis for heat transfer is third law of thermodynamics. And then the fifth example is the heat transfer concepts are widely used in radiators, heaters and coolers. Now all these three heat transfer concepts like conduction, convection and radiation, these are used in radiators. Radiators are nothing but these are the devices used to cool the IC engines in all the automobiles. So the radiator will cools down or it will remove the temperature from the IC engine. And heaters are the devices which are used to increase the temperature of a particular room or a chamber. So they will use some kind of heating device. They will use some heat exchanger to do this process. And coolers also, what we are using now as refrigeration systems. All these devices like radiators, heaters and coolers based on the laws of heat transfer, which is in turn based on the third law of thermodynamics. So far we have seen different laws of thermodynamics. First one is zeroth law, where when there are three systems are there, system A and B are in thermal equilibrium with system C. Then we can say system A and B are also in thermal equilibrium. And then first law, energy can neither be created nor destroyed, but it is converted from one form to another form. So this is law of conservation of energy. And then second law, the entropy of an isolated system always increases. When a system is isolated, the entropy of the system will increase. And then third law is the entropy of a system approaches a constant value as the temperature approaches absolute zero. So these are the four different laws of thermodynamics which are of key importance in the study of thermodynamics. Based on this, many applications and many other related subjects are developed. Suppose we take the example of third law of thermodynamics. It has opened a new branch of study called heat transfer. And based on the second law of thermodynamics, we have different engines because it directly relates the working of a closed system. Based on the second law of thermodynamics, we have developed many cycles like diesel cycle, Otto cycle, and in turn these cycles help to the development of engines, petrol and diesel engines. And first law of thermodynamics directly related to the conservation of energy. So this is all for today. We'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.